All right, welcome. Today we're going to be talking about tables and derivatives of tables. So just a quick table analysis. So let's just read the question and dive into our first couple examples. Make sure you take notes, and then I'll see you in the Zoom. So let f be a function defined for all real numbers x such that f prime of x is greater than 0 and f double prime of x is greater than 0. Which of the following could be a table of values for f? Okay, so they're asking me this question about f. And then they're giving me a bunch of information about f prime and f double prime. So they say f be defined for all real numbers, which just means, okay, we can plug anything into f. Nothing is kind of out of bounds here. Such that f prime of x is greater than 0. So let's say that the derivative has to be positive, right? A positive slope. And f double prime of x also has to be greater than 0. So that would be like the second derivative is also positive. If I had a graph, that would mean concave up, right? In this case, we don't have a graph. We just have a table. So we might not really be able to see what that looks like. And then working from there, which of the following could be the tables for f? So now we're actually just going to go through and we're going to see how we can find that from a table. Now, once again, we can't actually look for where the derivative is positive by looking above or below the axis, or concave up, concave down by looking where it's increasing or decreasing. We actually have to do some math here. All right, so our calculations are going to look a lot like they used to. So we're specifically looking for where the derivative is positive and the second derivative is positive. So let's just go through and see if this, for a, if the first derivative is positive. So I'm just going to find my rate of change. I'm basically finding change in y over change in x, right? That is a huge formula that we'll be using today, is actually calculating slope. And remember that you could use y2 minus y1 over x2 minus x1. Yeah, so there's a lot of different ways that you can use this. I'm just going to kind of take a look at our rate of change over here using this kind of method of change in y over change in x. So our y values are actually decreasing by 1. From -3 to -4 is actually a decrease. And on the other side, it's increasing by 1. So that actually tells me that -1 over 1 is -1. Now that actually can be crossed off because it tells us in the very first part that our derivative has to be positive. So we're specifically looking for something that has a positive derivative. We can cross off A. Now let's look at B. So B, we're going to go through the same process of doing our change in y over change in x. From -3 to 1, it actually increases by 2. Remember that that's getting closer to 0 further to the right on our number line over 1. So that is an increase of 2 over 1. And then from -1 to 3, if you count up, that's 4. Right, a slope of 4, and then from 3 to 19, that's actually a slope of 16. So you can definitely see that this is passing that kind of first restriction set by the derivative being positive, but we also need to find the second derivative. So one thing that I'm going to label here is this is going to be like my first derivative, right? Think of that as your slope. Now, this next second derivative is just finding the slope of the slope. So the second difference from 2 to 4 is an increase in 2, and from 4 to 16, that's an increase in 12. So not only is the first derivative positive, but the second derivative is also positive. So that tells me that my answer choice for this one has to be answer choice B. You can see my work off to the side, which is just finding my slope in each situation between each set of points, and then finding the derivative of that derivative, right? To find my second derivative. So that tells me that not only are we increasing, but we are also concave up in this problem. Okay. If you want to, you can go through and you can actually see why these are incorrect. And just really quickly, even though this one is going up by 3 for its first derivative, its second derivative is 0. And it says here, the second derivative has to be greater than 0. So while this is f prime, our f double prime does not work. And then similarly over here, this is going to be 8 followed by 6 followed by 2, and those second derivatives are actually negative, which tells me concave down, right? Which is not what we're looking for here. So once again, that doesn't kind of fit the requirements of the second derivative. So really, what we're looking at today is just kind of finding slope the old-fashioned way using this change in y over change in x formula, and you can actually get more specific by actually plugging in your x1, x2 values in, y1, y2 values in to this formula here, subtracting and dividing. All right, example 2. Let's see how this one is maybe similar or a little bit different. In this case, we are once again given the table of x and f of x, okay, and we are being asked questions about f of x again. So let f be a function such that f double prime of x is less than 0. So that's its second derivative has to be negative, right? Remember, less than 0 just means it has to be a negative number. For all x on the closed interval from 1 to 2. So we're just kind of including x's from 1 to 2. Selected values of f are shown above. Which of the following must be true? Now, the tough part is now they're asking us questions about f prime. And notice how every single one of these is talking about f prime of 1.2. This is basically the guts of the question right here. Okay, so let's just kind of look at where is 1.2 in our table. That's right here. And they're asking us what is the slope at 1.2. Well, we don't have an equation to actually find the derivative of and plug in 1.2 to find the slope. All right, but what we can do is we can approximate it by average rate of change. All right, and what I'm going to do is I'm going to actually take the average rate of change of the left to actually figure out how much is it increasing by to the left, and I'm going to find the average rate of change to the right, and then I'm going to see, okay, what are those approximations for the average rate of change? So if I find the average rate of change to the left, remember I'm just doing change in y over change in x, and f of x is really just another way to writing y. So to find my change in y down here, I could just do some subtraction. 4.38 minus 4.18. And some of you, if you're using a calculator, that's just going to give you 0.2. Now if I do 1.2 subtract 1.1, I'm going to get 0.1. And I think one thing to keep in mind here is that if you are using this formula, it's important to subtract 4.38 minus 4.18. Right? That's like y2 minus y1, and then x2 minus x1. So you're going in the correct and the same agreeable order when you're doing this. And once again, that gave us 0.2 over 0.1. Now, if you use your calculator for this, that just turns into a slope of 2. All right, just think about moving those decimals over in the numerator and denominator by multiplying by 10. And then similarly, we're going to do the math over here. So we're going to find the average rate of change between 4.38 and 4.56. So we're going to subtract, think of this as y2 and y1, x2 and x1. So 4.56 minus 4.38 over 1.3 minus 1.2. All right, now in something like this, we get 0.18 over 0.1, which turns into 1.8. Okay, so once again, that was kind of, if you want to see that, that was 0.18 over 0.1. So that gives us 1.8 as our slope there. Now, that's kind of what's happening around this value right here. We know it's not going to be the best and the most precise because this might not be linear. But if we kind of think about this, it's, it's very kind of like a slope of 2 as it gets up to it, and then it kind of slightly changes to like a slope of 1.8. So it's got probably some kind of curve going in there. But if we think about averaging those two things together, finding the average rate of change, that gives us a really good approximation for where f of 1.2 is going to be. So is it possible that the slope is less than 0? Did either one of my slopes give me less than 0? Was it a negative slope? Absolutely not. Is it true that our slope for 1.2 is going to be between 0 and 1.6? Well, if we think to the left and to the right, we got 2 and 1.8. Are either of those values in between 0 and 1.6? No. C, is the slope at 1.2 going to be between 1.6 and 1.8? I don't think so. Not according to my calculations. And then finally, could it be between 1.8 and 2.0? Yeah. All right, and this is kind of what all of this work is being shown up here using kind of our linear approximations. So when you're doing this work today, I want to see these formulas. And it's saying, show your work when possible. I want to see these formula calculations in some way, shape, or form. So if you've got to rewrite the table and then do those calculations, please do so. This is how we're just approximating slope from a table using first and second derivatives.